Hi everyone, I'm Jim from Tsinghua University, and this work is joint work with collaborators from NUS and Central South University. Today I will present Stream Bus. This achieves the network as a semantic virtual storage bus. This allows a modified application to run on demand from remote storage with near-native performance. Let's first look at how applications are delivered today. As shown here, users must download an entire application package before they can start using it. This is essentially an all-or-nothing model. Even if the user only needs a small part of the application, they still have to download everything, often hundreds of megabytes or even gigabytes. This all-or-nothing delivery model leads to two major problems. First, users often delay or avoid updates. As a result, no vulnerabilities persist, and developers' efforts are wasted. Second, application size keep growing. This leads to a long download and installation time and poor user experience, especially for short-term usage, such as travelers need a transit app or users trying a new released application. Both problems actually stem from the same root cause. Applications must be fully installed before used. To overcome this limitation, we need to rethink how applications are delivered. Traditionally, application follows static installation model where full installation is required before execution. But today's networks are fundamentally different. With high-speed 5G and Wi-Fi 6, the network can now provide bandwidth comparable to local storage. With high speed, this opens a new opportunity. We can treat the network as a storage bus and ultimately enable on-demand execution of applications without installation. Despite this promising opportunity, both industry and academia have explored many solutions. However, all of them face significant limitation. First, framework-bound approaches, for example, Google Instant Apps, require intrusive modifications to applications, making them difficult to deploy for existing systems. Second, web and mini program solutions simplify delivery, but rely on browser-based runtimes, which often sacrifice performance and native functionality. Third, network file systems like NFS do support remote execution at OS level. However, they are fundamentally designed for data access. They are optimized for high throughput and sequential access, but not for application execution. This mismatch makes them inefficient for execution-driven access patterns, such as unpredictable control flow jumps. So we can say that existing approaches fail to balance transparency, efficiency, and comparability. To achieve these goals, our key idea is a semantic virtual storage bus. The intuition is simple. Instead of treating storage as passive data blocks, we make it aware of application execution. Specifically, we capture execution context, such as which thread is running and how you access data. Based on this context, a semantic-aware prefetcher predicts future block access sequences, prefetches code block ahead of time, and streams it on demand. This enables what we call execution-aware streaming, effectively turning remote storage into a local execution-aware bus. As a result, application can run without installation, achieve low latency execution, and remain full compatible without modification. To enable on-demand application streaming, we face two fundamental challenges. The first is the latency gap. Modern processors require data at a microsecond level to avoid stalls. However, accessing remote storage over the network typically takes milliseconds, especially for the wireless networks such as Wi-Fi and 5G. This creates a 100 to 1,000 times mismatch, meaning the CPU often stalls waiting for data. The second change is the context gap. Storage systems are inherently stateless. They treat code block as independent requests, but application execution is stateful and thread-specific. Access patterns depend on control flows such as branches, loops, and interaction across threads. As a result, generic prefetching strategies cannot effectively predict future code block sequence, such as Linux default read-ahead algorithm. To address these challenges, we designed Stream Bus, a semantic virtual storage bus that bridges execution and storage. At a high level, Stream Bus sits between the application and remote storage and makes remote blocks appear like local or execution-aware stream. Okay, let me walk through the workflow. The application issues a read or trigger a page fault. Then the request is intercepted and sent to the runtime, where the fast parser immediately fetches the requested block. Based on this, the slow parse starts fetching predict blocks in the background while also fetching the requested block from storage. Finally, the requested block is returned immediately while the fast pass, while predicted blocks are streamed through the slow pass. Both request and prefetch blocks are stored in the page cache for future use. This dual-mode transmission marks network latency by overlapping on-demand fetching with background prefetching. We use Markov chain model here because it captures state transitions where the next state depends on current state. This aligns well with the program execution, where the next code block often depends on the current one. It is also lightweight, as prediction only relies on the current state without requiring long histories or complex model. Let me walk through this workflow step by step for the dual mode mechanism. First, when the application accesses a missing page, a page fault is triggered and enters the fast pass. Second, the fast pass sends a request to fetch the required block from the server. Third, the server responds with metadata indicating how many blocks should go to the fast pass and the slow pass. Fourth, based on this metadata, the client activates the slow pass for background fetching. Fifth, the server returns the required block through the fast pass for immediate execution. In parallel, predicted blocks are streamed through the slow pass in the background. Finally, once the required block arrives, execution resumes on the main kernel thread. According to this dual mode mechanism, the fast pass serves the current demand while the slow pass prepares future blocks. As a result, higher latency network accesses are effectively turned into the memory access, masking the latency. Now, let's look how we build the prediction model. We first collect block access sequence from different threads of the same application. These sequences are then merged to capture overall execution patterns. Next, we count transitions between consecutive blocks, building a count hash map of next state frequencies. Finally, we normalize these counts into probabilities, forming a Markov transition model. At runtime, given an application and a start block, we first locate the corresponding executable and its Markov model. Then we iteratively predict the next block based on the current state, generating a sequence of future successes. This process continues until we reach a predefined prediction length. By modeling execution context as a Markov chain model, we closely capture application access patterns, enabling accurate prediction with minimal overhead. Importantly, this is very lightweight. We can generate hundreds of future blocks in just milliseconds, with far less overhead than complex model like DNNs. We evaluate on both desktop and mobile devices under a standard 1 Gbps network. We also integrate stream bus into the Android framework, enabling unmodified Android applications to run directly from remote storage with only minimal system changes. We compare against the local storage and NFS using a set of representative real-world applications. First, let's see the micro benchmark. We can see the stream bus significantly improves prediction accuracy. As shown in the figure, we achieve up to around 40% higher cache hit rate comparable to both local storage and NFS. The improvement is essentially pronounced for applications like Shortcut and Android Studio, where access patterns are more complex. Second, on the desktop, stream bus can even outperform high-performance local storage under cold start conditions, reduce per-page latency by up to 16 to 40% compared to an NVMe SSD. This is because our execution where fetching effectively turns network I/O into memory access. Finally, on mobile, even over Wi-Fi, stream bus maintains a competitive performance. The latency remains within about 17 to 27% of local storage, which is a relatively small overhead given the feasibility of remote execution. These exceptions are mainly due to fragmented file layouts with many small files, which increase metadata access and reduce the effectiveness of prediction. Then we evaluate end-to-end performance under a typical workflow of download, install, and startup. On desktop, stream bus and FS skip download and installation, while on mobile, stream bus still requires a lightweight install due to Android system constraints. Compared to NFS, stream bus consistently reduce startup by 20% to 55% compared to local storage. Stream bus achieves near NVMe performance on desktop. And on mobile devices, it typically sustains startup overheads below 40% relative to local storage, even over Wi-Fi. There are a few exceptions, such as Shortcut on desktop and WPS on mobile, where performance drops due to fragmented layouts and less predictable access patterns. Moreover, for end-to-end application delivery, stream bus reduce total time by 45 to 78% on desktop and 36 to 18% on mobile compared to the native workflow. Finally, we evaluate robustness and network vulnerability. We inject round-trip latency from 2 to 100 milliseconds, together with packet loss and jitter to emulate realistic WAN conditions. The metric here is end-to-end delay, and the dashed line represents a local installation baseline. As we can see, stream bus performs well under intra-city latency around 2 milliseconds, where the performance is close to or below the local install baseline. Moreover, it maintains good performance under inter-city latency around 10 milliseconds, with most applications still below the local install threshold. This shows that despite increasing a network delay, execution-aware prefetching effectively masks the latency, keeping end-to-end performance stable. To conclude, Streambus enables applications to run on demand without installation through a semantic virtual storage bus. It effectively masks network latency, achieving near-local performance. Finally, we think this has the potential to enable zero install applications and edge cloud execution. Yes, thanks for your listening.